Hello to the programming team. This is an introduction to the Solubuddy program, an overview of what it's about, and try to bring your attention to some of the modifications that are needed and try to explain them in a systematic, understandable manner. Solubuddy program, the website, helps people with the process of making solutions. So what I'll do here is just describe what do I mean by that language. What is a solution? And when describing solutions, I often use the words solvent and solute. So we'll get around to making it very clear what's meant by those words as well. Okay. The word solution is used interchangeably with mixture. So solution is just a mixture. And the mixture is formed when you physically combined two or more substances. By physical combination, I mean they're just present in the same place at the same time. They just mingle. They haven't reacted with one another to form something new. Each component or identifiable substance in the mixture retains its own identity. For example, think about the air that you're surrounded by and are breathing. It's a mixture. There's some oxygen. I should mention nitrogen first because it's the most abundant component of the atmospheric mixture. The big two are nitrogen and oxygen, but then there's also other things like argon and lower levels of carbon dioxide, etc. Anyway, those are different substances physically combined. They just happen to be in the same place at the same time. And mixtures are extremely common, of course. Essentially, all the matter that you interact with is in the form of mixtures. Okay, so we put, say, two things together. Now, specifically, we're going to talk about solutions. We'll put together something that's called a solvent and a solute. So in this example, we're putting sugar into water, mixing it in with water. Okay, so where do these words solvent and solute come from? Well, you could say those words are quantitative, based on quantity. We follow a logical approach to decide which one we will call the solvent, which one we will call the solute. When we make mixtures, the materials that are put together are really, essentially never put together in equal proportions. Usually, there's a much greater amount of one than the other component or the other components. And so we choose that we will call the one a solvent if it is that substance that's present in the greatest quantity. Like in this example, water is a solvent if we put a gram or a teaspoon or something like that into water. You know, that mixture is 90+% water. We call water the solvent. And conversely, solute is, of course, then used to refer to that component of the solution present in relatively smaller or lower quantity. Here is a little concept map. Mixture made up of a solvent and a solute, one or more solutes. The solvent is a substance that is present in the greatest proportion. Here's some examples of solvents: water, dichloromethane, ethanol. That list goes on. Methanol, benzene, toluene, ethyl acetate. There's all kinds of different examples here of the solvent. Usually for the solvent, you choose the solvent and you get it from like a bottle of the pure substance. Okay. So the mixture contains a solvent and a solute, which is a substance that's present in smaller proportion. And you could say that the solutes are dissolved in the solvents because the accommodation of the solute in the solvent is kind of a chemical matter, and there's kind of intermolecular forces involved. But your program doesn't need to go into any of that sort of detail. The concept of concentration will be applied to the solute. We can use concept of concentration and some kind of concentration ratio to discuss how much of the solute is present relative to the mixture or the amount of solvent. I have a whole YouTube video. If you just go to YouTube and look up Kreller concentration units, you will see that I have a whole YouTube video describing concentration units, which are used to describe how much the relative amount of solute in solvent. Next, we will talk about the different forms that the solute can have or be in when it's pure before it's placed in the solution. Because actually, the form that the solute is in previous to mixing actually controls the way you will handle the making of the solution. Solute before mixing could be in the form of a pure solid, pure liquid, or it could be in a concentrated stock solution. So we'll just talk about these first two for now. We'll have to make a future video to describe the concentrated stock solution when the solute is present like that. But anyway, back here, when the solute exists as a pure solid, if we know what substance it is in pure state, we know the molecular weight for it. And so we just figure out how much we have to weigh out. Here's the calculation for determining the mass of the pure solid that would need to be added. We would need to multiply the concentration of it. So if it's here in units of molarity, it's the number of moles per liter of the solution. So assuming that the solute doesn't really take up or change the volume in any way, we just multiply the concentration, the molarity of the solute by the volume of the solution. And then those two factors multiplied together give you the number of moles of the solute that are contained in that volume of the solution. And then that number of moles, to convert it into its mass, we would multiply by the molecular weight of the solute. Now let's go on to talk about the cases that need to be considered in which solute is a pure liquid. The operation of making the solution then has two possibilities. We could transfer that liquid by mass, very similar to the way we transferred pure solid by mass. Maybe we can just weigh it out. It needs to be contained in a pure solid, but just keeping it in a little beaker might be good enough. If it's not too volatile, turn really rapidly into gas, maybe we can just weigh it. So that operation really looks a lot like the process of weighing a solid. But the pure liquid, obviously it's fluid, it can flow, and we can transfer it by volume. So let's take a look at the calculation of how it would be determined, or how we would figure out how much volume is needed. Calculating the mass of pure liquid, as I mentioned, is just multiplying the number of moles by the molecular weight. Well, that looks the same if it's by mass. If it's what's called a gravimetric transfer. But if it's a volumetric transfer, we calculate the volume of it that we're going to add, and then we use a volume measuring device to transfer. Basically, the calculation looks very similar to those shown previously. First, we calculate the number of moles of that solute that exists in that volume of solution by multiplying its molarity by the volume. Then, the next step, I guess, is the same again. Now that we have the number of moles of the solute in that volume, we calculate the number of grams of it by multiplying the number of moles by the molecular weight. But to calculate the volume of the liquid that corresponds to, we need another factor, conversion factor being the density, the number of mils per gram of that substance. Basically, that's how you calculate the volume to do the volumetric transfer. Now let's just take a look at the actual website, Solubuddy website. Now I think you might have a little more background as to like what you're looking at or what this will do, why it has these different regions. Okay, so this first box is for all the in cases in which you're preparing a solution, one solution maybe. There's some solute that you're going to be adding to the mixture. And this is asking you, in what form is the solute? Okay, and here's the choices. It's a pure solid, I will add it by mass. Where's the other choices? Oh, there they are. It's a pure liquid. If you choose that, you know, these options pop up that are based on the information that you have about it. If all you really need to know about the liquid is its molecular weight or its molecular mass, and you can weigh it, you will do a gravimetric transfer. Or if you know its molecular weight and you also know its density, because you know that you're going to have to transfer it by volume, you can choose this option. Okay, let's go back. Pure solid. Okay, if it's a pure solid, you choose that. And that'll be, I imagine, a pretty popular way to go. Okay, so it's a pure solid. Solvent. Okay, here's one change. The solvent formula can be just solvent name, because for some things this was programmed to calculate the molecular weight from formula, but we never need the molecular weight of the solvent. Sure, it's nice to know what it is, but you don't need to know it. You don't calculate the concentration of a solvent. So solvent formula, that can just be changed to solvent name. Let's put in water. Okay, solute formula, NaCl. Well, that's in number 4, so it remembers that. Solute molecular weight. Now, the program remembers that entry as well. It asks for molecular weight, but in the background, it's been set up so that it calculates molecular weight from the formula. And actually, it's been programmed to sort of test the molecular weight that the person enters at this point against the molecular weight that it has calculated from the reference atomic weights. And if there's an error later caused by that incorrect molecular weight, the program will tell the person. Okay, total solution volume in mil. Let's put 1,000 for that. Okay, solution concentration. Okay. Well, the program has enough information now to calculate the concentration of this sodium chloride solution in water. You know, it knows the total volume. It knows the molarity. Okay, if we say it's 1. Okay, now it knows the total concentration and the molarity and the molecular weight. So now it knows everything that it needs to know to calculate the mass. But it's asking the person, what's the mass of solute to add? Okay. Let's put 58.44 because I've done this 100 times before. Okay. So we know this volume, and we're going to gravimetrically transfer some solid. So you see we've got rudimentary graphics here. Next. Okay. Okay, so I guess there's no error message, so this must be complete, and it was programmed to tell the person the steps that would be followed. It's a little overdone, it's a little bit redundant to have these steps plotted out, but I don't think this is the largest error in the program we have to worry about. see where we can save that solution or print it. Let's go back. Formula again, that could be named. It's not going to work. Well, gravimetrically adding a liquid. So why don't I say that I'm putting some methanol, CH3OH, in there, because that is a liquid when it's pure. Solute molecular weight. Okay, well, I'll just guess that it's 12, 15 to 16. Let's add arguments, try 32. Again, let's try 1 mole per liter, mass of solute. So there's solute to add. So it should be exactly 1 mole, because it's 1 liter concentration, 1 mole per liter. So 1 mole, which has a mass of 32 grams per mole. So 1 times 32. Let's try that. Now here are these pictures. We didn't get to the point where we sort of customize these pictures. This could be liquid, or we could do without these graphics altogether. I think it's kind of a complication. So let's go down. Okay. That calculation must have been accurate enough. Or let's go back. Let's make a mistake. Chosen mass is 16. Error is 50%. You should go up. So it was programmed to give some hint as to what was going on if the person was wrong. Okay. Well, click on this to go back to the home screen. Let's add it by H, wait, use 32 again. Density of pure solute. Wow, okay. If we're doing the volumetric transfer, here it is. We need the density. Okay, so let's just over here. Believe everything you see on the internet, but I'm just going to grab a value, 0.792. Okay. 2 grams per mil. 1,000. This illustration, we'll just put that 1 volume solute to add. 32 times 0.79 is 2. don't know if I was actually wrong somehow, or if there's a bug. Okay, but anyway, that's as much a video I'm going to prepare today. I will continue with another installment if you think this is a good approach, or whatever. We'll just communicate and see what more information you need. I do need to, one way or the other, go over the higher functions. Comparing multiple solutions with serial dilution, comparing different sets of calibration standards. But hopefully this little video installment has been useful. Talk to you soon, guys.